Hello, welcome back to three-phase circuit analysis. Here we're going to tackle our first lesson in delta three-phase circuits. So here we have the circuit on the board. It's our first of a couple of them. And by now you're going to find out, as we've been seeing all along, that once we have the core concepts of three-phase current and voltage shifting, doing the different configurations is really just kind of doing the same things over and over again. So before we had Y circuits, then we had Y delta circuits, then we had delta Y circuits, and now we have the final configuration delta delta. This is what a full-blown circuit would look like. But I want you to notice, first of all, that it's very simple for a few reasons. First of all, in the source side, we have our voltage sources, but we don't have any source impedances here. So the problem's a little simpler because we don't have any source impedances. Notice the three lines here that connect the source and load. There are no line impedances. So this is assuming a perfect circuit with no losses in any of the transmission lines going from source to load, and with no losses inside the generator itself. So it's kind of an idealized problem to kind of get us started here. So we have a delta source connected to a delta load. Each phase of the source has a magnitude, well, it looks like I have a typo right there. This is not 1200, this is 2400. They should all match. So we have 20, this is 2400. So we have one of these phases has an angle of 0, the other one's minus 120, and the other one's plus 120. So it's a balanced three-phase set. And then over on the load side, we have the load impedances, and they are balanced impedance. It says right here, the load is balanced with an impedance of 200 plus J 150. So what this means, that's this impedance here, and this impedance here. So we have a balanced three-phase source, we have a balanced three-phase load, and we're asked to find the following things. We want to find capital AB, capital BC, capital CA, the currents in the load, in other words. Notice the loads have the capital letters, the sources have the lowercase letters. So we want to find the current through here, and through here, all three of them. And then we also want to find the three line currents. These are the three line currents we've been finding for every problem so far. And then we finally want to find the source currents, BA, CB, and AC. Now notice again, I told you when we talked about delta sources that because of the way it's all drawn, you can go back and look at my lessons on that, but basically the current between here, because it's a source and we know the current's going to be going this way, we actually call that IBA instead of IAB. So it's BA, and then the same thing here. Normally it would be AB, BC, CA. That's what we do for loads, but everything's backwards. AB if you read it backwards, BC if you read it backwards, CA if you read it backwards. So when you read these source currents, they're the same exact currents that we've been finding all along. It's just the reference directions are backwards because these are sources and the current needs to be going this way, like this, AC and BC and CB and so on. All right, so first things first, how are we going to find this guy? Normally, for the currents in the load here, normally we're going to draw a single phase equivalent circuit and all of that. Normally we need to do that. However, this is a very simple case, so we don't need to. Because we don't have any impedances here at all, what you know is that the voltage between A and B is physically connected to this source, to this load over here, Z, and all of these are the same, so it's connected across here. So because you know the voltage drop physically across here, you can calculate the current directly. You don't need to write any single phase equivalent circuit because there's no impedance here at all. In other words, there's no drop here at all. So all of this voltage lies entirely across this phase of the load. So the way that you handle that is, let's see, where's the best place to put it? I guess I'll go over here to the right. You know the voltage is 2400 angle 0. You know the impedance is given by this in the problem. So we can write down for part A, we'll want to find that current there. We can say that I, capital A, capital B, right, is going to be the voltage drop from A to B. Notice the polarity plus minus. So this is plus minus over here. So it's that 2400 angle 0. And you're dividing it by the impedance of the load, which is the same, 200 plus J 150. All right? And so when you do that, you find out that I, capital AB, when you do this division in a calculator, get 9.6, angle negative 36.87 degrees amps, and it's RMS. I'm probably going to forget to write that. RMS it's true for all of these guys. So this is one part of part A. We didn't have to write a single phase equivalent just because this circuit was a little simpler. We found one phase. Now, just like any other problem, once you know one phase, you can find, for instance, the A phase. That's the A phase current, AB, IAB. To find BC or the B phase current and the C phase current, you just add and subtract 120. So in order to do that, we have to go back to our problem and figure out what is the phase sequence of this problem to know if we're going to add or subtract 120. So we look and we say, well, the A phase is going between A and B. That is 0. Okay. So you can say, normally we label it AB, but we'll call it, well, just to make it easy, we'll just call it AB. Okay. And then, so that's AB, right? And then we go and look and say, well, what's the next phase? From BC here, that's the B phase of the load, that's at negative 120. So that's at negative 120. And the C phase goes between A and C, that's at positive 120. So we'll call it CA. And that's at positive 120. So you have to look at each phase there and label them so that we know this one is negative 120 from this one's positive 120 from this, and to read the phase sequence, we start here and we go around. So it's an A, B, C phase sequence, so it's a positive phase sequence. Positive phase sequence. Meaning that when we start up here with a phase current, in order to find the B phase, any of the B phase quantities, we're just going to subtract 120, and any of the C phase quantities, we're just going to add 120. So the reason why we care about that is because the next thing we're going to do is find the B phase, which is going to be, so it's AB, so it's going to be BC, it's going to be the same magnitude, negative 3687, and because it's a B phase quantity, we just said we're going to subtract 120 degrees from it. So IBC, 9.6, angle, when you do that subtraction, you're going to get negative 156. 87 degrees amps. It's RMS. I'm not going to write RMS every time. And then thirdly, so AB, BC, capital CA, the other third phase, 9.6, angle, we start back at our root, negative 36. 87, instead of subtracting, we're going to add 120 degrees. So CA is going to be equal to 83.13 degrees. And that's, of course, amps RMS. So BC is negative 156.87, and CA is 83.13. So this is very simple, because essentially what we're doing is you have a delta-delta. You need to recognize you don't really need a single-phase equivalent circuit. You could draw one if you want. But quickly you'll find that this voltage is what lies across this load, so we can find this current. Once we have the A phase current, we can find the other two simply by adding, subtracting 120, knowing what the phase sequence is. We get the phase sequence from the generator. All right, so the next part of the problem says, we found all of these three. Now we want to find the three line currents. That's AA, BB, and CC. We want to find all of those. So let's, again, just like always, we're going to focus on the A phase line current and figure out that one, okay? So if you remember, once you know the currents in your delta load, you can use a shifting formula to find the currents in the line. So as I'm trying to teach you generally how to do all of these problems, basically you can shift voltages or currents. If the voltages are the same between line and phase voltage, line voltage, you don't need to shift them if they're the same. If they're different, then we have a voltage shifting formula. Same thing for the currents. If the current, phase current, line current are the same, you don't need to change them because they're the same thing. But if the phase current, line current are different, then you have a current shifting formula. So you know from looking at this that this line current is going to be different from this phase current, so you have to use a shifting formula, and you know what this current is now. We just found it. So we'll use that shifting formula to go from phase to line. And what is that formula? We're going to write it down. We've used it many, many times. Should I do it here or there? Let's just do it right here. We've done it many, many times. Basically, for part B, we're going to shift, and we're going to say that IAA, which is a line current, is equal to square root of 3 times the phase current, IAB, and I'm verbalizing it out loud because it's kind of how I want you to remember it, with a phase shift of, this is the only hard part to remember, it's either minus plus 30 degrees, with the minus sign on top, the plus sign on the bottom. So it's basically a line quantity here is the square root of 3 times the phase quantity here, right? So I'm going to kind of have just kind of showing you that that's a line quantity and the phase quantity. And the phase shift is flipped upside down, plus or minus 30. If this were the voltage relation, then it would be very similar, except you would have plus minus 30 over here. All right. So because of the way things are going here, we don't need all these words to solve our actual problem. So we'll kind of take that way and use our space. Now, because we know it's a positive phase sequence, we choose the upper sign, which means this is going to be a negative 30-degree phase shift. And look, from our previous lesson, we already know what the phase current is. We stick it right in here, and then we can shift and get our line current. So AA is square root of 3 times this AB, which is 9.6, angle negative 3687 degrees. That is the phase current. And then we're going to shift that by negative 30 degrees. So we open up a new parentheses. You can either write it as 1 at an angle of negative 30, or you can just kind of leave the 1 off because it's implied there. But ultimately, when you write it down, you realize what you're doing is multiplying whatever's outside of the phasors, and then you're just going to be adding these phasors together. You can do it in your calculator, or you can do it by hand. What you're going to get when you multiply all these guys together is you're going to get a magnitude of 1663. And when you do this, you're going to get a phase shift of negative 6687 degrees. And that's the line current. And that's amps RMS. All right, for the phase current, same sort of thing. BB, you're just going to start with the A line current that you had, 1663, angle negative 6687. Now, what do you do for a B quantity? Just like before, when you start from an A, you subtract 120 to get to a B quantity because of this phase sequence. Right? So then you're going to get BB 1663 angle, and when you subtract this guy, what you're going to get is, oh, let me get the right thing here. Yeah, you're going to get negative 186.87. Okay, this is the answer for the B line current. And then for the C line current, ICC, start again at the root of A, 1663. Angle negative 6687. Instead of subtracting, we're going to add 120. So ICC is equal to 1663. I know it's boring just adding numbers, but this is what you're going to do on a test. 5313 amps. Okay, so now we have the A phase line current. Let me double check myself. Negative 66.87. The B phase line current, negative 186.87, and the C line current, 5313. All right, so we have done part A. We shifted the currents to find this current for part B, but then we add, subtract 120 to find the other two. Now, how do we find the generator current? This is where a lot of students get confused. It doesn't really matter if you're at the source side with the delta or the generator side with the delta. When you can still shift, use the exact same equation. Nothing is different about using the shifting equation to go from a line current to the phase current. Whether you're at the load side or whether you're at the source side, it's exactly the same equation. Just the labeling is a little different because of what I told you about here with BA being basically kind of a reversal of the letters, but the actual math is the same. The A phase line current is related to the A phase current in exactly the same relation. Okay? So what we're going to do is write that down. Now that we know the line currents, we can shift to get the phase currents on the generator end inside that triangle, each of those guys. So what we're going to do is we're going to remember, I'm going to write it down in words. It's a line current is the square root of 3 times the phase current. And you shift by either minus or plus 30 degrees. Minus or plus 30 degrees, but we know it's a positive phase sequence, so we can take away this. So we know it's a negative phase shift of negative 30 degrees. So if we're going to write it in terms of our variables, the line current for the A phase is AA, square root of 3. What's the phase current on the left-hand side of that triangle for the A phase? Normally we would say it's IAB, but because it's a source, the labeling is a little backwards, so it's IBA. But it's the same thing, it's just going the other way in the triangle. So IBA, this is the phase current, and then we're going to shift that by negative 30 degrees. Now remember, we know what this line current is now. We just calculated it. This is what we want to find, the phase current for the A phase in the generator. So we need to rearrange this equation to solve for what we want to solve for. So if we're solving for this, IBA is going to be equal to let's do it this way, 1 over the square root of 3, because we're taking this over here, AA, right? And then when we divide by this phasor on the other side, remember it turns into a positive 30 degrees. We've talked about that many times. When you divide by this phasor on the other side, you're changing the phase shift because it's an exponential, and so on. You can go look at the other lessons as to why we change it when we do it. But this is what happens when you rearrange this equation. Now we can actually plug in the line current that we have, and we can calculate the phase current in that A phase of the triangle. And for this, let's see here. Yeah, okay. For this guy, I want you to think IAB. In other words, I'm so used to thinking AB, BC, CA that I just want you to think that this is really kind of a backwards nomenclature. Usually for the A phase, you think AB. I'm just telling you that you got to reverse that when you write it down. I mean, it's not going to be totally wrong. You're still calculating the same quantity, but to be totally right, you should reverse it there. So this is what goes in the equation, but in your mind, you can think, oh, this is A phase, AB, okay? So the next thing we're going to do is plug in the value of AA, the line current that we calculated here, 16.63, and an angle of negative 66.87. So we will say IBA, the A phase current, square root of 3. Then we're going to plug in 1663 angle, negative 6687. All right? And then we're going to shift it by positive 30, just like we talked about here. So I'm just going to kind of write it as positive 30 inside here. Okay, now we can do all the math. You multiply these and you add these together. So IBA is going to be 9.60 at an angle, negative 36.87 degrees. And that's amps. That's the A phase current for the generator side. Okay, so this BA here, this is the current coming out of the source right here, okay, in that leg of that triangle. Just like always, the phase current, the phase sequence is a positive phase sequence, so we know how to add and subtract 120 appropriately to get the other phases. None of that has changed. So you got to ask yourself, what would the B phase be? If that's the A phase, what would the B phase? Well, normally it's A, B, B, C. So BC is the B phase usually, but we reverse it, we call it CB. So you should write down CB. So ICB, that's the B phase current, 9.6, and then you start with what you had, negative 36.87, that's the A phase current, and then you're going to be subtracting 120, because to get the B phase, you're subtracting 120. So CB, 9.6, angle. What do we have here? Let me make sure I did my math right. It's going to be negative 156.87 degrees. Okay, that's the B phase current in the generator. Now the C phase current, again, normally it's IA, B, B, C, CA. The C phase usually is CA, but it's reversed in the source. We call it AC. AC, 9.60. Start with the same root, 36, negative 36.87, but for the C phase we add 120 because of this phase sequence here. 9.60 angle, what do we have? 83.13 degrees. CA, 83.13 degrees, and that's amps. That's it. So again, lightning fast through this problem. We know what this voltage is, so we put it across the load. We calculate this current, right? Once we have that current, we can subtract 120 and add 120 to get the other phases of that load current, okay? Then we go back to our A phase and we shift from this A phase current into this A phase line current with the same shifting formula we always use. It's a line current is a square root of 3 times phase current with a phase shift. We chose the negative sign because it's a positive phase sequence. Once we calculate the A phase line current, then we can subtract 120 to get the B phase and add 120 to get the C phase, as we always do. Then we say, okay, well now we have these three line currents. How do we go from this A phase line current to this A phase current? I guess it's going this way. It's exactly the same equation. You say the line current is a square root of 3 times the phase current with a phase shift, negative 30, because it's a positive phase sequence. So this is line current, square root of 3, phase current, right? Now we rearrange the equation to get it into the form, so we're calculating this phase current, which is this quantity. We rearrange everything, and we plug in the value for the A phase that we had to get the A phase generator current, phase current. That's what we get. And then same exact thing. To get the B phase current, we subtract 120. C phase current, we add 120. One thing I want to call your attention to, look at these phase angles. In the generator side, for the A phase, the phase angle of the A phase was negative 36.87. Now look at the load phase angle for the, where's it at? For the load here. The load for the A phase, negative 36.87. That was the load current. Okay. Now look at the load current for the B phase was negative 156.87. The generator B phase also had a phase angle negative 156.87. Now look at the C phase, and the generator current was 83.13, and the C phase for the load was again 83.13. So for this particular problem, the delta phases for the currents in all branches of that triangle on the generator side were exactly the same as the phases on the load side. So for this particular problem, the way it was set up, the generator phase angles match the load phase angles for every phase. They all match exactly. That's not always true, and that's basically because there's no impedance in the line. So everything's completely symmetrical, right? You have some sources, you have some loads, everything's balanced. So that's why it's that way. If you have different impedances in the middle there, then things are going to be a little bit different. And I want you to notice further that the magnitude of the generator current, 9.6, right, is the magnitude, also matches 9.6 magnitude of the load current. Now, why do you think that's the case? I mean, the magnitudes of the generator current matches the magnitude of the load current, and the phase angle of the source current for every phase matches the phase current of the load current for every phase. Why do you think that's the case? It's the case because this is the equivalent circuit of just having a battery connected to a resistor. You're going to have some current coming out of the battery. It's going to go over, and that's going to be the same current going through the resistor. And the voltage drop across that battery is going to be the same as the voltage drop across that resistor because they're physically connected to one another. If you just look at the A phase, the current's coming out of here, however it splits, it goes through the line current. And since everything's symmetrical, this current's going to match this current in magnitude and in phase just because of the symmetry. When you put a line impedance, a real line impedance in the way, then you have a voltage drop across there, and that it can change the phase and it can change the magnitude as well. So it's a good check on what's going on here. But it's important for you to know that that's not always going to be the case. So this was kind of an intro problem, the delta-delta. We're going to do one more of these things to kind of give you some practice. Follow me on to the next lesson, and we'll do that right now.